On the topic of limit of a function, when you're calculating the limit of f of x as x goes to a, if the limit exists, it's equal to L, G, or a value. The limit of a function is defined as follows. Suppose function f is defined for all x near a value like a, except possibly at a. If function f of x is close to L or G, this number here can be represented by L. For all x that are very close, right? As you can see, on the left-hand side, on the right-hand side, you're getting closer and closer to A. On the vertical line, your f is getting closer and closer to G or L. You can call it any number that you like. Then we say that the limit of f of x as x goes to a is nothing but L or G or that y value on y-axis. So when we introduce the topic of sequences, we are interested in analyzing the behavior of a sequence. Is a sequence convergent, divergent? What is the limit of that sequence? The sequence a sub n converges to a number like L if for every positive number like epsilon, you can find a corresponding integer n such that at some value, at some numbers, n, which is more than n, you can conclude that the difference, the distance between the terms of the sequence and L are very small. So this happens on y-axis. And this happens on x-axis. That's the main difference between them. If you cannot find a fixed value, a unique value like L, then we say that, hey, the sequence diverges. If sequence an converges to L, we write down the limit of an as n goes to infinity is equal to L, or simply an approaches L. But again, please note that this is on y-axis. L is called the limit of the sequence. This is basically the same thing that you did for regular functions. You find the limit, and if the limit exists, you say that, hey, we have a convergent sequence. Otherwise, you say that we have a divergent sequence. So take a look. The initial behavior of this sequence is very random. We don't know what are they doing. Are they going up, down? Are they converging? Are they diverging? So you need to skip the finite numbers of terms at the beginning of the sequence and just look at the end behavior. That's why n goes to infinity. When n goes to infinity, you look at the behavior of your terms or the y values. As you can see, these are getting closer and closer to y equals to L. For example, take a look at this sequence and its terms just in flat line, horizontal line. When n is equal to 1, you have 1. N is equal to 2, you have this number which is between 1 and 2. Then you have a sub 3, when n is equal to 3, it is this number here. When n is equal to 4, you get 2. Okay, what's the behavior? It's a little bit difficult to see what's going on here. We prefer to see and visualize this in 2D. When n is equal to 1, your square root of n is equal to square root of 1. When n is equal to 2, get square root of 2. So this is 1, this is square root of 2, then you get square root of 3, then you get square root of 4, which is 2. And if you take the limit, of square root of n as n goes to infinity, is basically taking the limit of square root of x as x goes to infinity, which indeed is infinity. So since it is not a number, guys, infinity, it's not a number. It's just a representation for a very large integer or a real number that we don't know what that is, but it is not a unique number to say that, hey, the limit is infinity. Not a unique numerical value. So by definition, this sequence is a divergent sequence. It goes to infinity nonstop. So now that we define the limit of a sequence, we want to analyze other types of sequences. For example, 1 over n. In 2D, when you plug in 1, you get 1 over 1, which is 1. When you plug in 2, you get 1 over 2. When you plug in 3, you get 1 over 3, 1 over 4, and so on. So the y values starting at this point, and they are decreasing. So if I ask you to find the limit of 1 over n as n goes to infinity, it's the same as asking you to find the limit of 1 over x as x goes to infinity. 1 over infinity is equal to 0, so we expect the limit to be 0. And you see the behavior. This sequence is decreasing, and if you continue plugging different values, you get your y value to be 0. So it's an example of a convergent sequence. It's all about the end behavior of your sequence. Again, you can skip the behavior of the finite numbers of terms at the beginning because they might be oscillating or they have a weird or random behavior. We are interested in seeing when n is large, when n goes to infinity, what's the behavior of the sequence at the end, toward the tail. Now take a look at this sequence. an is -1 to power n plus 1 times 1 over n. Okay, in 2D, we can visualize it this way. When n is equal to 1, n equals to 1, you get -1 to power 2, which is 1, and you get 1 over 1, which is 1. So this is the very first y value. The second y value, if you plug in 2, you get -1/2. Okay, now I got a negative y value. So far, I see that it was here, then it decreases to this point here. If I plug in 3, I get a third, which is this point here. Then it goes up, then it goes down, goes up. But it seems like these numbers are getting smaller and smaller in size. This sequence converges to 0. If you find the limit of -1 to power x plus 1 times 1 over x, later on I show you that we have a nice theorem. Instead of working with -1 to power x plus 1 times 1 over x, we can find the limit of the absolute value as x goes to infinity. The limit of 1 over x as x goes to infinity is 1 over infinity, or 0. So we expect the limit of this sequence goes to 0 as well. It means that you have a convergent sequence. Next example for you. We want to find the limit of n divided by n plus 1 as n goes to infinity. This is basically calculating the limit of x divided by x plus 1 as x goes to infinity. This is equal to, well, as you remember, what you can do, you can divide the numerator and the denominator by n to simplify this as much as you can. N over n divided by n divided by n plus 1 over n. Okay, when n goes to infinity, let's simplify this first. You have, if you cancel out n and n on the numerator, you get 1. N and n on the denominator, you get 1. So this is just 1. This is just 1. And you end up with 1 over n. This in turns is equal to limit of 1 divided by the limit of 1 plus limit of 1 over n as n goes to infinity. But remember that this is nothing but 1 over 1 plus 0. Why is that? You get 1 over infinity, which is indeed 0. So the limit is equal to 1 over 1 or 1. What's the meaning of that? It means that this sequence, a sub n, which is n over n plus 1, has a limit, has a unique limit. So it is a convergent sequence. What about this sequence? an is equal to n divided by square root of n plus 10. So in order to find the limit of this sequence, you're basically doing the same thing as elementary calculus. This is equal to the limit of n divided by n, which is equal to 1, over the square root of 10 over n squared plus n over n squared, which is 1 over n. Now, basically, if you take the limit as n goes to infinity, this is equal to 0 because you get 10 over infinity plus 1 over infinity, which is indeed equal to 0. Okay, see what's happening here. You have 1 divided by 0, which is equal to infinity. But what's the meaning of that? It means that you have a divergent sequence because the limit is not a unique number. We can also use the method of L'Hopital's rule. Suppose f and g are differentiable on open interval I containing a value like a. Suppose the derivative of g on the denominator is not 0. If the limit of f and limit of g are both equals to 0, also if you have infinity over infinity, so this is one of the case, 0 over 0, or if you have infinity over infinity, the limit of f of x divided by g of x is the limit of f prime of x over g prime of x. This is called L'Hopital's rule that they used in elementary calculus. Suppose you are interested in calculating the limit of ln of f divided by n as n goes to infinity. Well, the limit of ln of x divided by x as x goes to infinity is equal to the limit of, applying L'Hopital's rule, you get 1 over x, which is the derivative of ln of x, divided by the derivative of x, which is equal to 1. But this guy indeed is equal to 0. You get 1 over infinity, which is 0. So this is the method of L'Hopital's rule. Whenever you have 0 over 0 or infinity over infinity, you can indeed use it in this example. In this example, the limit of ln of x divided by x as x goes to infinity is infinity divided by infinity. So we use the method of L'Hopital's rule to calculate the limit of this sequence. So you can conclude that the limit of ln of n divided by n as n goes to infinity is equal to 0. What's the meaning of that? Since you have a unique number as the limit, you have a convergent sequence. What about the following sequence? an is -1 to power n. Is it convergent? Is it divergent? Do you have a unique numerical value as the limit? First of all, let us list the terms of this sequence. If n is equal to 1, you get -1. If n is equal to 2, you get 1. If n is equal to 3, you get -1, and so on. These terms are oscillating between -1 and 1. an doesn't approach any fixed number. If you look at the behavior of this sequence, when n is equal to 1, you get -1, and it jump up to 1, jump down to -1, jump up to 1, jump down to -1, and so on. The limit of -1 to power n when n goes to infinity doesn't exist. You cannot say it is 1 or -1. Which one is that? We have no idea. The sequence -1 to power n is divergent. The terms are oscillating between -1 and 1. Since it doesn't have a unique fixed value, it is a divergent sequence. The theorem says if the limit of absolute value of an as n goes to infinity is equal to 0, then you can conclude that the limit of the sequence itself is equal to 0 as well. Let us evaluate the limit of -1 to power n divided by n. What are we going to do? Instead of working with the sequence itself, we're going to work with the absolute value of this sequence. The limit of absolute value of -1 to power n divided by n as n goes to infinity is indeed the limit of 1 over n as n goes to infinity. But this limit is equal to 0. 1 over infinity is equal to 0. So since the limit of the absolute value of an is equal to 0, you can conclude that the limit of an is equal to 0 as well. So this is the behavior of the graph. As you can see, if you just take positive values, you have a decreasing behavior in your sequence. If you take the negative y values, again, you have an increasing behavior. It means that the end behavior are the same. They are going toward 0. So here you have a convergent sequence. It means that it has a unique numerical limit. As you can see, it is equal to 0. Remember squeeze theorem from elementary calculus. The squeeze theorem says if you have 3 functions, an, bn, cn, if the limit of an and cn are equal to each other, and they are both L, then you can conclude that the limit of the middle function is equal to L as well. So what's the use of it? You can use this to evaluate complicated or complex functions limits. So in this visualization, you have a behavior for an. This is a known function or known sequence. Also cn. cn also is a known and a function or a sequence that you already know how it behaves. bn, however, might be a more complicated or complex function or sequence that behaves like this. Well, you see it goes up and down, up and down. Where does it go? So you're squeezing bn between 2 other functions that you already know how to deal with. This is the gist of a squeeze theorem. We find two functions that we feel comfortable working with, an and cn, and as long as this complicated function, complex function bn is bounded between these two, the behavior of the limit of bn is the same as the behavior of the limit of these two functions that we already know how to deal with. Well, question says find the limit of the sequence bn, which is cosine n, divided by n squared plus 1. Well, this is more of complicated function. It's not very familiar to me. I haven't seen this regularly in book or in examples. It's not basically a parent function. So if I can squeeze it between two other functions, then maybe I can find the limit of this a little bit easier. This is the behavior of cosine of x. Remember that the domain of cosine is negative infinity to positive infinity. Its range is bounded between -1 and 1. It means that my cosine gets the minimum value, -1, the maximum value, 1. So, since cosine of n is always bounded between -1 and 1, I have a lower bound and upper bound for this function. Well, okay. Now positive in solving this problem. Why is that? Because -1 divided by n squared plus 1 is less than or equals to cosine of n divided by n squared plus 1, which is less than equals to 1 over n squared plus 1. Well, what we did, we divided everything by n squared plus 1. So now you have two functions or two sequences that you already know how to deal with. If you take the limit of an, it is equal to 0. It is equal to the limit of cn, which is also 0. By squeeze theorem, you can for sure say that, hey, the limit of the middle function must be equal to 0. So the limit of this function, cosine n divided by n squared plus 1 is indeed equal to 0. So it is convergent. Suppose you're interested in discussing the convergence or divergence of sequence an, which is n factorial divided by n to power n. Well, an can be written as 1 times 2 times 3 times 4 times 5 times n, which is the definition of n factorial, divided by n to power n. It means that n is multiplied by itself n times. You can also rewrite an as 1 over n multiplied by 2 times 3 times 4 times n divided by n times n times n times n. Why it is helpful? First of all, note that this guy is less than or equals to 1 over n. Why? What's the reason behind it? This quantity here, which is the multiplication of 2 times 3 times 4 times 5 times 6 times 10 times 100 times a million, is less than, divided by n times n times n times n, is less than 1. Note that, guys, here 2 is less than n. 3 is less than n. 4 is less than n. Or you can just add equality as well. So if I multiply 2 by 3, by 4, by 5, and the rest of them, it must be less than or equals to n times n times n times n. So if you divide both sides by n times n times n times n, on the right-hand side, you end up with 1. This is equal to 1. So this quantity is less than equals to 1. So 1 over n times 1 is less than equals to 1 over n. Now, an, or the sequence that you have, is bounded between 0 and 1 over n. It is not a negative number, and it is not equal to 0, right? What's the meaning of that? It means that we can apply the squeeze theorem. We know that 1 over n as n goes to infinity is equal to 0. The limit on the right is 0. The limit on the left is 0. So the limit of the middle function must be equal to 0 by using the squeeze theorem. The limit of 1 over n as n goes to infinity is 0. The limit of the constant function 0 as n goes to infinity is always 0 by squeeze theorem. The limit of the middle function must be equal to 0 as well. That's the use of squeeze theorem. When you have crazy looking functions, you need to find the functions that you already know how to deal with. As long as you can squeeze your complex function, complicated function between two simpler functions, then your life is much more easier in evaluating these types of functions. And this is the behavior of this graph, which, as you can see, is decreasing from the maximum value to the minimum value. After 10, they're getting closer and closer to 0. And we have a theorem listing some important sequences and functions and their limits. The very first one is the limit of ln of n divided by n as n goes to infinity, which is always equal to 0. You can apply L'Hopital's rule to find the limit of this function. The second one is the limit of the nth root of n as n goes to infinity. It is 1 as well. 3, the limit of x to power 1 over n as n goes to infinity, considering that x is positive, it is equal to 1. Number 4 is the limit of x to power n as n goes to infinity, assuming that x is bounded between -1 and 1. This is always equal to 0. Number 5 is the limit of 1 plus x divided by n to power n, which is exponential function e to the x. And number 6, the limit of x to power n divided by n factorial as n goes to infinity is equal to 0 for any x. So students find these 6 limits a little bit useful to remember when they are completing their homework, writing their exams. And to calculate each one of these limits, you can go back to elementary calculus and use the techniques that you learned over there.